If you could imagine the best switch ever made, the world's ideal switch, what would it include? Zero on resistance? Instant on and off? Would it be made of GaN? Why, yes, it would. And no, the ideal switch isn't reality yet. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Zobair Roohani from Infineon and I explore the fundamentals and characteristics of wide band gap materials. We also investigate why the higher band gap and higher electric field withstanding capability of GaN brings us closer to that ideal switching technology, and the unique design challenges one must pay attention to when driving GaN devices. And before we get started, don't forget to click that link. There you can find even more information about this topic from Infineon. Hi, Zobe. Thank you so much for joining me.
Thank you, be with you.
So, we're talking all about GaN today, but before we get started, what all will we be covering today?
So today I'd like to cover gallium nitride HEMT, high electron mobility transistor, which is a wide bandgap switch. And I'd like to begin our discussion by covering its fundamentals, ways we can drive it, best methods to lay the devices on our board, and outline some performance expectations of GaN versus existing silicon. And finally, I'd like to also highlight some updates in terms of latest development using gallium nitride technology.
Zobe, can you set the stage for us? What are the characteristics of a wide bandgap material?
To best understand the advantage of GaN as a wide bandgap device, it is useful to draw a comparison of highlighted semiconductor characteristics on this slide, namely the bandgap, breakdown field, electron mobility, thermal conductivity, and electron drift velocity. And so I'll go through each one so we can better understand each metric. So we start with the band gap. The band gap is an amount of energy required to pull electrons from the valence band into the conduction band. And the higher the band gap, the higher the electric field withstanding capability of the device. In fact, actually, the higher the capability of the semiconductor, even at higher temperature. The breakdown field, or also the critical field, determines the minimum amount of material before arcing can occur across the device. And the higher the breakdown field, the smaller the device may be. Electron mobility is a metric of how easy electrons can move within a material. Obviously, the higher the electron mobility, the less the resistance the moving electrons will experience within the material. And the thermal conductivity is intuitive. It is the ability of material to allow for heat transfer within the material. And the higher the thermal conductivity, the easier heat can travel through the material. And finally, the electron drift velocity, it is the average velocity an electron can reach when an electric field is applied. And the higher it is, the faster and easier electrons can move within the material. And so, as we can see on this chart shown in different colors, silicon in gray, silicon carbide in green, and GaN in purple, we can see that GaN exceeds the rest of the technologies by far, especially when it comes to band gap and breakdown field, which makes it a great switch, a wide band gap switch.
What are the consequences of higher electric field withstanding capability for a WBG device?
Higher band gap and higher electric field withstanding capabilities enable us to get yet another step closer toward that ideal switch, which has zero on resistance and can turn on or off instantaneously. And we'll take advantage of this very simple and yet useful schematic to highlight the GaN advantage. In this diagram, a 650 volt potential is applied across a silicon device housed in the blue box on the left and across a GaN device housed in the green box on the right. The blue box is intentionally drawn larger as the silicon semiconductor requires a much larger mass to support the same electric field. On the other hand, since the GaN has a higher band gap energy as well as higher electric field withstanding capability as discussed previously, To support the same electric field, it requires much less mass. And this has profound advantages. That is, electrons now can travel through a shorter distance, which means less conduction losses. And moreover, since we have a smaller die, an overall capacitance associated with a small die would also be smaller, and it will allow it to have faster transitions and therefore lower switching losses. And at the system level, what this means is that now we can switch at faster rate, we can have less conduction losses, so the system can enable higher power density and potentially even lower cost.
Zobair, inside that green box, you showed a GaN device. So, how is the structure of a GaN device different from a silicon one?
For that, let's take a look at this more detailed cross-section of a GaN. At first glance, it is evident that unlike a vertical silicon device, which was shown in the previous slide, a GaN HEMT is a lateral device. That is, current flows horizontally from drain to source. The next immediate difference factor is the heterogeneous structure of the GaN HEMT, as GaN device is built on silicon as the substrate, and interestingly, it only takes about 5 micrometer to grow the GaN device on top of the 200 micrometer of a silicon substrate. And the choice of silicon as a substrate has been a critical factor in commercialization of GaN, since silicon is cost-effective. And equally important, existing silicon fabs can be used to manufacture GaN without additional investment in new equipment. Next, there is a transition layer in between GaN and silicon substrate to account for the differences in thermal coefficient of expansion, as well as crystal mismatch between the silicon and the GaN. But the real magic happens when aluminum gallium nitride, AlGaN, is deposited on top of the GaN layer. Due to crystal strain in nanometer distances, and these are very small distances, and piezoelectric characteristics of GaN, a two-dimensional electron gas forms between the two layers, so that when an electric field is applied drain to source, current flows within the device. However, since in power electronics applications, normally off-device is desired, a P-GaN, either in the form of an ohmic PN junction or a Schottky, is added to locally reduce the crystal strain and the piezo effect and pinch off the channel. This allows the device to normally stay off and only turn on when a positive voltage is applied at the gate. A second P-GaN is added near the drain to mitigate trap charges, which otherwise led to on-resistant variations when device is dynamically switched. This issue is referred to as dynamic RDS on, which is now resolved by this structure shown here. And finally, the drain, gate, and source metallizations are added to form the 3 terminals of the device. So this lays out how a cross-section of a GaN would look like. And here on this slide, it's a very nice drawing of GaN die shown on the left, where the source and drain buses are highlighted in green on the left and the right side of the die, and the small gate pad, which is shown at the very bottom. And then the middle image shows the die, how it is soldered on the back metal tab, and wire bonds are attached to the drain paddle on the top, and the 2 wire bonds which are used to connect to the gate and the Kalman source connection. And finally, as shown on the very right, the device is completed by epoxy mold injection, as shown here. It is important to note that unlike the majority of silicon devices, the large back metal substrate is connected to the source terminal as opposed to the drain.
What would a GaN HEMT look like on a schematic level?
So as highlighted, there are 2 main flavors of E-mode GaN. There is the ohmic GaN as shown on the left and the Schottky GaN, P-GaN on the right. The 2 diagrams highlight the parasitic structure of each device, and indeed they are very similar. So let's take a look at the ohmic GaN, P-GaN first. So all the components inside the dotted box are internal to the GaN HEMT. The inductor external to each terminal, that is the drain, gate, source, and the Kalman source, are parasitic inductances associated with the immediate circuit board traces around the device. At the heart of the diagram is the diamond-shaped current source, which highlights the two-dimensional electron gas we mentioned in the previous slide between the drain and the source. And the two resistors in series, one on the top and the other on the bottom, signify the on resistance of the channel. And given the physical proximity of the gate to the source, the bottom resistor is a smaller portion of the overall on resistance. And then very similar to silicon devices, and the CGS, CGD, and CDS, which are the parasitic gate to source, gate to drain, and drain to source, respectively, represent the parasitic capacitances of the device. And then the immediate resistor at the gate terminal is the internal gate bus resistance. And the series resistor and the diode from the gate to the source highlight the PN GaN or the PGaN structure. And forward biasing of this diode allows the device to turn on and remain on. And that is why this structure also is getting the designation GIT, or the gate injection transistor. And finally, the reverse stack GaN diodes are accounted to protect the gate from the negative spikes. And turning over to the right side, the Schottky P-GaN structure is indeed very similar to the GIT, except for the highlighted Schottky connection at the gate. But it does require a different applied VGS voltage, which is actually making it more of a similar device to a silicon device.
Okay, so Zobair, what should a designer expect in terms of driving a GaN switch?
We will utilize the schematic and the waveforms in this slide to answer this question. The schematic shown on the left shows the gate driver inside the smaller box on the left, which connects to the GaN GIT switch, which is also shown inside a dotted box, through a simple network of passive elements. To best address this question, it is helpful to examine the VGS versus QG behavior of the GaN device, which is shown by the turn-on waveform in the middle of this slide, with x-axis being the gate charge and the y-axis being the VGS itself. Throughout this segment, it is helpful to keep in mind the structure of the GaN switch, highlighted in the dashed box, by the way. Given its lower gate threshold, VTH, typically a negative voltage is applied when the device is off. So the turn-on process begins from the applied negative VGS. And as VGS rises, the applied source charges the CGS capacitor, the gate-to-source capacitance, that is. And at the VTH, the device starts to conduct current drain to source. And then at the QGS point, the CGS capacitor is charged, and the device starts charging the gate to drain, or the Miller capacitance, and hence the designation on the y-axis of V Miller. And finally, VGS is clamped by the internal PN diode from the gate to source. So immediately looking at the gate current graph on the very right, the first peak that we see there is the one that shows the amount of charge that is carried by the gate driver to source the entire QG total. And this happens when the S1 inside the gate driver closes. The current flows through the R on and the CC to provide this initial pulse of current into the gate. And then in order to keep the device on, there's a small amount of current that continues to be sourced and injected into the gate through the RSS resistor. And finally, at the turn-off, the gate driver turns S1 off and turns S2 to sink current from the gate through the CC, R off, and the diode D off. This process will repeat itself in reverse. And so it's worthwhile to note that the gate of the standard silicon device, as well as a Schottky gate GaN, will have a similar VGS to QG and IG versus time waveform, minus this steady state current phase that is highlighted on the right for the GIT device.
Would the schematic for driving Schottky P-GaN be different?
The short answer is yes. And the differences are very subtle to extent where a unified layout with component populated options can be used for driving both Schottky gate as well as the GIT GaN. On this slide, for example, we have carried the GIT gate drive circuit from the previous slide on the right side, and the gate drive circuit for a Schottky gate is shown on the left. Since the steady state current is not needed in the case of the Schottky gate, the RSS resistor is shown in gray. However, two back-to-back Zehners are added to protect the gate of the Schottky GaN device from excessive positive and negative voltages. And contrary, in the case of the GIT, these Zehners are shown in gray and would not be needed because the PN gate structure itself actually clamps the voltage, and there exists the series clamping diodes, as shown in the previous slides, to clamp the voltage in the negative direction. And so at the Infineon, we call this circuit arrangement, which can be used for both the Schottky gate as well as the GIT gate, the easy drive circuit, which allows the use of the same PCB layout to drive both Schottky gate as well as the GIT GaN.
So, are there any other unique design challenges that we should pay attention to when driving GaN?
Yes, indeed. I would say the undesired turn-on at first pulse might be the most important to cover in our allotted time. To best understand the issue, we will review a typical half-bridge arrangement shown on the left side and its behavior through the waveform shown on the right. As you might know, this half-bridge is a common building block for many power converters or inverter topologies, and there is a lot of information embedded in it in the waveforms shown here. And we'll do our best to quickly review this behavior as it helps to better understand the dynamics involved. So looking on the diagram on the left, when the S2 at the time T1 pulls the gate of the high side low, a negative voltage is impressed at the gate of the switch, while capacitor CC retains its charge. The switch node waveform at the bottom initially jumps to slightly above the bus voltage V plus by initial negative voltage VNI, plus the V threshold of the high side GaN device. This is to allow for reverse current to continue to flow. After the allotted dead time, when the low side switch turns on at the time T2, the green switch node takes a hard transition leading to a brief undershoot. Now looking at the high side VGS top graph through the charge distribution of the CGD to the external capacitance CCC and the parasitic capacitance CGS, the negative voltage shifts slightly from the initial negative voltage to the VN. But if you pay a close attention here at this instant, there's also a slight spike at the gate of the high side noted by the VGP, which is as a result of current injected into its gate impedance through the Miller capacitance CGD. This spike must be less than the V threshold of the high side switch. Otherwise, it could lead to an undesired turn-on, leading to a momentary short from the bus voltage V plus to the ground. Throughout the time where the high side remains off, the negative gate voltage decays, as shown again by the top graph, and the rate of decay is determined by the RC time constant of the RSS time to CSS. At the time T3, when low side turns off, the switch node shoots up, incurring an overshoot determined by the load current and the loop inductance. And the negative load current leads to a transient undershoot at the high side gate as well. And finally, at the time T4, top side gate is turned back on. Now imagine, due to a circuit operation such as an initial turn-on or perhaps in burst mode operation, for example, the bottom side gate turn-on was skewed as shown by the waveforms in blue. That is when we turn on the low side gate when the top side negative gate voltage has decayed to near zero. The resulting spike due to Miller effect, which we just covered earlier, could lead to the undesired turn-on in this case as well, leading to a shoot-through condition, which could manifest itself as increased switching power dissipation for the system, or in worst case, it could actually lead to catastrophic failure. And in fact, in this slide, the waveforms on the top left again highlight the decaying negative VGS, which makes the device susceptible to this undesired turn-on. And this is shown in the graphs A. And the waveforms B and C show idealized conditions, which indicate not only an immediate negative voltage to mask the spurious event, but also an available negative VGS after required elapse of time. The diagram on the right shows a universal gate configuration for GIT and Schottky gate transistor, which utilizes a bipolar power supply for the gate drive, typically a plus 8 volt or a 6 volt for positive turn on, and a negative 3 volt for turn off is utilized. In this manner, whenever a gate is pulled low, it will always remain at the minus 3 volt, allowing for ample headroom for a reliable turn-off state, despite possible spikes due to the Miller effect.
Okay, so it sounds like parasitic elements within a circuit can alter its behavior significantly. So, why is this? And is there a way to eliminate or reduce parasitic elements?
That is very correct. Indeed, parasitic elements, especially inductive elements to a more extent than capacitive, can lead to undesired circuit behavior. To best explain the reason and offer solutions, let's formulate a statement of problem. And to do so, let's quickly examine the various parasitic structures present in a typical battery-operated three-phase inverter shown here. As you can see, there are parasitic inductances in series with the source, in series with the battery disconnect switch, in series with the shunt resistor at the bottom, and of course, embedded in the structure of each half bridge. Since the highest speed transients occur within each half bridge, let's take one half bridge, in this case, the green one, as an example. At the PCB level, such a half bridge is constructed using either through-hole or surface mount devices as shown here. Given its unique physical layout, each half bridge design will end up with a certain cumulative loop inductance, which is a summation of PCB trace inductances as well as parasitic inductances internal to each device. So considering a standard inductor equation, which stems from the Faraday law, the equation being V equals L times di dt, a quick calculations leads to understanding the significance of the parasitic loop inductance, especially when it comes to fast switching devices like GaN. So assuming a hard switching half bridge constructed using through-hole devices with an overall loop inductance of about 10 nanohenry and a current rate of change of about 10 amp per nanosecond, we arrive at a 100 volt overshoot, which for a system that operates from a 400 volt bus, this constitutes about 25% overshoot. And so the significance of this overshoot for a system is that it could actually either compromise the longevity of semiconductors used in the system, or in worst case, sometimes it could lead to catastrophic failures. And this forces the designers to actually slow down the switching of the semiconductor, which works against then the efficiency of the system, and it will increase the losses.
Okay, so is there a better method to mitigate the overshoot due to loop inductance?
Yes, indeed, there is. And it would help if we examine some of the fundamental concepts associated with inductance, particularly the loop area and loop inductance. So there are two loops comprised of discrete inductors shown here. One closely mimics a circle, and the one on the right looks more like a fork-shaped strip line. In the circle shape, there is little to no mutual inductance. As such, the total inductance is the sum of individual elements themselves. On the contrary, with the fork-shaped loop on the right, due to magnetic flux coupling between the opposite elements on each side of the fork-shaped loop, there is a higher mutual inductance as shown by the equation at the bottom, And rightfully, it subtracts from the total inductance. This leads to a much lower overall inductance in the loop. This concept can be used to reduce parasitic loop inductance in a power converter half bridge as well.
How does this translate in terms of physically laying out the GaN device packages on the board?
To put that in perspective, let's take a look at a simple half bridge arrangement, both in the form of a schematic as well as a physical layout as shown here on the left side of this slide. So examining a best case traditional method of constructing a fundamental half bridge block using these through-hole TU247 devices, we can place the high frequency decoupling capacitors C1 and C2, for example, on the blue pads, which extend to the Q1 through the yellow polygons. And in turn, the Q1 source, you can see, is connected to the drain of the Q2 on the right side through the turquoise color inner layer, and eventually to the source of the Q2, which is then connected to the ground plane, which completes a circuit by returning back to the C1 and C2 on the top layer. And a typical power loop inductance with such layout could be in around 15 nanohenry. And as noted earlier, with fast switching devices, this could result to an overshoot of about 100 to 120 volt. And now, instead of through-hole devices, if we construct this half bridge, let's say using surface mount devices, an optimized layout where the discrete parasitic elements could have an opportunity to mutually couple provides an opportunity to reduce the overall loop inductance. Here is a cross-sectional view of a half bridge realized using topside cooled SMD devices where power flows from the top right through the components and top layer traces and returns back to the decoupling capacitors through the immediate inner layer of the PCB. This arrangement allows for the magnetic flux coupling between the inductor elements on the top layer and the bottom layer, resulting in higher mutual inductance, which in turn leads to lower loop inductances. Here are two examples using bottom-cooled TO leadless package and another using the topside TOLT package. While in both cases, the loop inductance is considerably reduced. For example, in the case of the TO leadless, it's only 6 nanohenry, and in the case of the TOLT, 5 nanohenry. In the case of the bottom side TOL package, the return path is still not fully coupled with the top inductive elements, since space needed to be allocated for the thermal vias to take the heat away from the devices through the board. However, in the case of the top-side cooled devices, as shown in the bottom, as well as previously discussed in the top image, there is a full utilization of mutual inductance coupling, which naturally leads to lowest overall loop inductance.
Okay, so considering the availability of silicon, GaN, and silicon carbide devices on the market today, how do you decide which one is the best fit for a specific application?
The best method is to compare like device characteristics from each technology. This chart shown on this slide outlines characteristics of similar RDS-on devices at 600 or 650 volt from each technology, that is silicon, silicon carbide, and GaN, through the various figure of merits, that is RDS-on times QoS, RDS-on times QRR, and so on. These figure of merits provide a normalized mean to draw practical comparison of various characteristics of these devices. The lower the figure of merit, of course, the better the performance of the device. Here, for example, we are comparing around 50 milliohm devices, as noted on the third column. The RDS-on might vary, but these are the closest matched devices from different technologies. And the CoolMOS 7, C7, and CFD7 are silicon superjunctions. In the last two rows are the CoolGaN and CoolSiC, which are the GaN and silicon carbide devices, respectively. And so let's examine these various figure of merits to better understand the advantage of one technology versus the other. So looking at the RDS-on times QoS, for example, this characteristics allows a time-related assessment of how fast output capacitance of the device can be commutated. As seen in the corresponding column, both GaN and silicon carbide are almost an order of magnitude less than silicon CoolMOS devices. With this characteristics, wide bandgap devices, especially GaN, enable the next higher level of switching frequency in resonant converters, hence allowing for a higher power density. Next, looking at RDS on times QRR, which signifies the ruggedness of the device in hard commutation topologies such as continuous conduction mode totem pole power factor correction, or even in resonant converters such as LLC, where special operating points such as startups or fault events might lead to hard commutations. So since GaN has no minority carriers to be cleared and therefore zero recovery charge, it provides the ultimate performance in this category. On the other hand, looking at the RDS on times EOSS, which is a critical figure of merit, especially for single-ended topologies such as classic PFC or flyback converters, and it signifies the dissipated energy stored in the output capacitance of relevant devices. And so while the GaN advantage is not as profound compared to the other two figure of merit we just reviewed, it is still outperforms the silicon as well as the silicon carbide. Finally, looking at the figure of merit on the very right, RDS on times QG. So QG is the amount of charge source or sunk at each switching cycle, and the lower it is, the lower driving losses, which are significant of total power losses, especially at higher switching frequencies and at light load conditions. So overall, it is clear that the GaN across all figure of merits outperforms all other semiconductor technologies. And the return could be even maximized when it is used in most suitable topologies as the one that were noted on this slide.
Is there a practical limit in maximum allowable switching frequency using GaN devices?
Indeed, there is, and designers must conduct early assessment in this regard for best results. That is acceptable power density and yet manageable thermals. The Pareto-front analysis example for this 3 kilowatt telecom converter shown on this slide puts this best in perspective. Let's begin first as a reminder to our audience of what Pareto-front is, which is basically a set of Pareto-efficient solutions generated by a multi-objective optimization process. That is, for each set of assumed inputs and settings, best performance is achieved. So as noted earlier, on the right is a Pareto-front analysis for a 3 kilowatt telecom power supply. This graph on the y-axis designates efficiency, right away maybe power loss. Then on the x-axis is the power density, or another way to look into the x-axis is switching frequency. So the more you are on the right, the higher the switching frequency. So the result for the GaN is shown in a gray color Pareto-front, and the Pareto-front for the silicon is shown in black. And this analysis includes all power electronic components, auxiliary electronics, PCB parasitics, and even a 20% additional volume being added to account for non-ideal placement of components. So for example, in this case, if you take the 96.7% efficiency and draw a horizontal line to cross both the gray and the black, we can see that the GaN technology enables almost 30% higher power density at this same efficiency point. Another way to look into this as well is that at the same power density, you can achieve a much higher efficiency with GaN as well. So if you look at the 72 watt per inch red line, we can see that the efficiency for the GaN is near 97.5, while for the silicon it still remains at 96.7% efficiency. And so while this analysis clearly shows the GaN advantage, it is important to note that even with GaN, there are limitations, and beyond a certain power density, that is a certain maximum switching frequency, there will be degradation in efficiency.
So, GaN transistors have been in production for a while, but what are the latest developments? And are there any unique devices on the roadmap to watch for?
I agree. And while improved GaN switches so far been introduced compared to the silicon devices, they are in a way similar to the existing devices. So one of the latest unique development utilizing GaN is the monolithic bidirectional switch. At Infineon, we are on the onset of introducing two versions of these monolithic bidirectional switches. One, which is designated on this slide as dual gate BDS, is the high voltage version. And the other is the single gate BDS, which is the mid voltage in the range of 40 to 200 volt. So the dual gate BDS, the high voltage variants, this device can operate in bidirectional mode in which it can conduct current in both direction or block voltage in both direction as well. Or it can also operate in a diode mode when one gate is on and the other is off. This device has two independent gates shown on the circle on the left top. It is a monolithic merger of two HEMT devices which share the same drift region. Internally, the two devices share a common drain, and it also features a substrate management circuit which sequences depending on the mode of operation of the device. So the single gate BDS is the low voltage variance. It only enables the bidirectional mode and is also a monolithic merger of the two switches, but in a common source arrangement. So overall, the BDS devices will provide an opportunity to replace multiple devices, up to 4, the relevant application, leading to not only space and power loss savings, but potentially cost savings as well.
What kind of applications can benefit from such a bidirectional switch?
So these are examples of immediate applications which could benefit from the use of GaN and BDS devices. For example, in the server market, it can enable significant board savings as well as power loss savings when used as a load disconnect or in ORing functions. In the consumer applications highlighted on the top right, for example, with the continued proliferation of USB on the go, MBDS can serve as a load disconnect switch, which can obviously conduct current in both direction and block voltage in both direction, necessary for a USB device which allows power flow in both directions. And the energy storage systems and BMS systems, such bidirectional switches can enable the next level of power density when used as a battery or load disconnect switches.
Okay, so being such a unique and versatile switch, are there any innovative approaches in the power electronic field to take better advantage of this kind of switch?
Indeed, there is new opportunities to increase power density in existing topologies such as current source inverters, or opening the frontier to explore new topologies such as matrix converters. Here on the left side is a high voltage GaN MBDS driven by two independent gate drivers and corresponding aux supplies. Such an arrangement can replace two back-to-back silicon or silicon carbide devices in current source inverters, as shown on the top right, allowing for higher efficiency and a higher power density. And both academia as well as in industry has begun on new topologies such as matrix converters, which allow for a direct AC to DC isolated and power factor corrected power conversion, which eliminates the need for an intermediate bus capacitor, for example. With the advent of the bidirectional switch, there are opportunities to take advantage of GaN, utilize new topologies to better address power conversion needs in a more efficient way and enable the next power density levels.
All right, so to wrap things up, Zobe, can you recap your main points for me?
Absolutely. So we reviewed and understood that GaN as a wide bandgap device enables superior switching and conduction performance versus both silicon and silicon carbide. The E-mode GaN is available in both Schottky gate as well as the PN gate, also called the gate injection transistor. We understood that a unified gate driver configuration can be used to drive either Schottky gate or the GIT gate. And understanding that the eGaN has a lower V threshold at its gate, it's important to mitigate undesired turn-on, especially during the first pulse events that we reviewed, by using proper gate biasing approaches. And for best utilization of GaN switch capabilities, it is beneficial to take advantage of flux cancellation in mutually coupled power traces to minimize power loop inductances when we are laying out our boards. With GaN having a superior figure of merits, it enables hard switching topologies such as totem pole PFC and allows for higher switching frequencies in resonant converters such as LLC. We also reviewed a Pareto-front analysis that shows that indeed GaN enables the next level of power density, but it is prudent to be cognizant of its limitation as well, as beyond a certain switching frequency, efficiency degradation is to be expected. And finally, we reviewed very briefly the next available exciting devices in GaN technology, the monolithic bidirectional switches that not only enable higher efficiency in existing topologies, but provide an opportunity to look into more advanced topologies, such as matrix converters, to further simplify and enable higher power densities.
Excellent. Well, I think that's all I have time for today. Thank you so much for joining me.
Thank you for the opportunity to speaking with you.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Infineon. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talks section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.